This is lesson 6.7, and I'm going to teach you about the applications of derivatives. So for the past couple of videos, I've been actually teaching you techniques on how to do a derivative, like how do you find a derivative, but what are they actually for? And so they actually have a lot of real life applications, such as urban planning, so we can look at population growth. We can look at business, like profit growth, revenue, and so on. Anything that has to do with growth, because if you think about it, growth is a rate and derivatives are a slope. Slopes are rates of change, right? So derivatives are slopes, are rates of change, are growth. Okay, so anywhere where you're actually looking at some sort of a rate, you're actually doing the derivative. So let's just jump right into it. Example number 1. A demographer, which is someone who studies demographics, like studies human populations and so on. A demographer developed a function to model the population P of a town T years from today. So T represents the number of years, P represents the population. They've given us the original function. Okay, and let's just read the question and see if we understand what they're looking for. A says determine the current population. So what is the population? If you're looking for P, they must have given you T. But it doesn't look like they've actually said what T is. So you really have to be able to go into the words and decipher that current is telling you about the time. Current means right now. And right now means time is 0. The initial time, like right at the second. What is the population? So that's pretty easy. All you do is you sub in a 0 wherever you see a T. 6,500, whoa, can't get rid of that. 500 minus 0.25 times 0 squared plus 235 times 0. Okay, it looks like we're actually trying to find our p-intercept, and that's going to be 6,500. So after all of these word problems, you got to make sure that you put a therefore statement. Therefore, the current population is 6,500 people. Okay? Now B is saying, what is the current growth rate? So the rate of growth of the population. They're not really asking about the population anymore. They're actually asking about the rate of growth. So the rate automatically triggers my understanding of they must be asking for the derivative, right? So if they want the growth rate, they're probably asking for P prime. So why don't we find P prime first? P prime is going to be the derivative of each of the terms. So the derivative of 6,500 is 0. Doing the power rule, we're going to take the 2 times the negative 0.5, 0.25. Negative 0.5 is my answer. And then I get t to the power of 1. Okay, this t has a 1, and so multiplying it down, plus 235, and that t has a power of 0, which makes it disappear. So this is my growth rate function. Now, they didn't ask for just a function. They actually want to know what is the current growth rate. Okay, so again, that word current means when time is 0. So the growth rate right now is when I put 0 into my t, and I get 235. That means I'm going to put a therefore statement. Let me just move up a little bit. Therefore, the growth rate, so we got to write it as a rate, is 235. Now, what does that actually mean? You're comparing your dependent variable, which is people, right, over your independent variable, which is time. Okay, so your growth rate is 235 people per year, blah. Okay, let's try the next one. Give yourself lots and lots of space. All right, so what's this asking us now? C, will the population ever stabilize? Oh, okay, stabilize. Stabilize is an interesting word. So stabilize means no growth. As in, your population does not go up or down, it just stays at zero. In other words, your growth rate is equal to zero. Okay, so we're going to solve for that. Our function before, let me pull it out again. P prime t is equal to negative half t plus 235. We're going to set that equal to zero so that there is zero growth, as in it's stable. And then we're going to kind of solve for the time and see if there is actually a time, like a certain number of years that go by, that maybe this zero growth rate exists. So bring that over to solve for t. And then you're going to get t is 470. So that means that in 470 years from today, you're actually going to get a stable population. Okay, so we actually answered the first question. I didn't write a great therefore sentence, but I'm sure you guys can. Will the population ever stabilize? Yeah, it will in 470 years, theoretically. If so, what is the population? Well, now they're not asking for the growth anymore. They're actually asking for the population. So that's going to happen at this year. And so the population at 470 years from now is going to require that same original formula, 0.25 470 squared plus 235 times the 470. Okay, which equals to about 61,725. And again, a nice therefore statement. Therefore, theoretically, the population will stabilize at 61,725 people in 470 years. Okay, now what that note says at the bottom is make sure that, this is all theoretical. Make sure that you understand the difference between theoretical, statements, and then also what could be potentially realistic or more empirical. Like, use your own common sense, use your deductive reasoning, because like a population that started off at 6,500, then in 470 years becoming 61,725, you just want to make sure that that actually makes sense. Even though it follows a theoretical, like mathematical model, like, will the town even have enough resources to become that big? Does it have enough finances? Will aliens come down and destroy them? I don't know. Right? So you never know. That's not very realistic, is it? Anyways, moving on. Okay, so business applications. Now, I'm not super business techie, so I am going to try my best to explain this. All right, let's just talk about t-shirts. And let's say that X represents the number of t-shirts. So a cost function, and by the way, I'm going to try my best to remember all of these different color codes so that I can use them for the next couple of examples. The cost function represents the function of how much it costs to produce the t-shirts, so how much it costs to make the t-shirts, depending on how many t-shirts you actually want to make. So the independent variable is your number of items, so the number of t-shirts, and then your dependent variable would be the cost to produce them. Now this one's a little bit more tricky. A marginal cost is the rate of change of that dependent variable versus that independent variable. Okay, so let me give you an example. Let's see. Let's say that you have a business and you're making t-shirts. You obviously have to buy the materials you need to make the t-shirt, like say the fabric, the cotton. Depending on like how much you buy, might change the cost of the production. Okay. And so let's say that you want to buy a lot because you actually have a lot of demand for your t-shirts. If you're going to buy more and more fabric from a company, they might change their cost for you because they might be like, oh, you're actually buying a lot. I'm going to give you a deal. If you buy this much more, I'm going to give you a deal. And that's going to affect the total cost of your actual production of your t-shirts. So this is what we call a marginal cost. Now, the demand function is obviously the price that you decide to sell your t-shirt at depends on the demand. So if you're selling a t-shirt and all of a sudden like a bunch of people want to buy your t-shirt, you're going to be like, hey, I can get more money out of this. Let's jack up the price. And so the demand function, by the way, little p, okay, little p, is just dependent on how many items you can actually sell. So usually what happens is the more you can sell, the higher you're obviously going to make your item cost. Now the revenue function is made up of two different things. So first of all, you have to take how many t-shirts you sell. And you're going to obviously multiply it by how much each of those t-shirts are. When you take how many you sold, so let's say you sold 100 t-shirts, and you multiply it by $5 a t-shirt, you're going to make $500. Did I say 100 t-shirts and $5? I hope so. I'm just saying stuff. So $500 is your revenue. All right, so it's based on your price and then obviously how many you're actually going to sell. Now, the marginal revenue is again that rate of change with respect to the domain. So the domain is going to be, not the domain, sorry, the dependent variable, which is your revenue, over your X, which is the number of units sold. Okay, so basically the change of your revenue is what the marginal revenue is actually calculating. Okay, so there's a couple other ones. Your profit function, again, very easy to understand. Your profit is whatever amount that you ended up making when you took your numbers sold. So if you sold that 100 t-shirts for $5 each, you made that $500. Technically, not all of that is profit because you have to subtract however much it costs to make the t-shirt. And so that cost function was our original, like from the very first function we talked about, C at X, was how much it actually cost to make this t-shirt. Okay, so the marginal profit, again, is the profit with respect to the number of items that you actually sold, but it is the rate of change of that profit. Okay, so I kind of explained it a little bit further down here. Change in profit with respect to the number of items you sold. So again, if you sell more items sometimes, someone might give you a deal on materials. It might change your profit because it might affect how much it costs you to actually make that t-shirt. And of course, a lot of times we don't really talk about DX, like the number of items. A lot of times we actually talk about time. And so if we're going to talk about the profit with respect to the change in the number of years that you actually have your business, we would switch it to DP over DT. And notice that these two are going to be capital P's. So the little p is for that price function. Okay, so let's take a look at some examples. Example number 2. Quinton Mills produces flour. So the estimated cost in dollars of producing X bags of flour is, and then they gave you the function, the original function. Okay, so again, I'm going to try to use the same colors that I used before. This is the cost function, and that is the function that describes how much it actually costs if they're producing a certain number of bags of flour. So they're asking to find the marginal cost. Now remember that the marginal cost, and you can look back at the video, marginal cost is C prime at x. Okay, and they've actually told you what x is. So x is 1,000 bags. All right, so let's start off first by finding C prime. Okay, so we're going to take the derivative. This is going to become 0. This is just going to become 0.43. And then the 2 is going to multiply all of that. Let me make sure I get enough zeros. How many zeros is that? 1, 2, 3, 4, 5, and a 2. And then an x. Okay, so there is my function for the marginal cost, but I want the marginal cost at 1,000 bags. So 0.43 plus 0.000002 times 1,000. All right, and I'm getting something like this. So what does that actually mean that I just found? Well, when I've sold about 1,000 bags, the change in my cost of producing those bags of flour is going to be $0.432. Okay, because it's a marginal cost, right? But since it's a rate, because it's a derivative per bag. In other words, when 1,000 bags of flour are produced, the cost is increasing because this is a positive number, increasing at a rate of 0.432, so about 43 cents, 43.2 cents per bag. Okay, now find the actual cost of producing the 1,001st bag. So the actual cost was the original function, actual cost. And there's talking about this one, C, and we're going to figure out when x is 1,001. So if you just plug in 1,001 into the original function, I'm not going to show you all that work, I get a number like 140,431.432. So remember that common sense deductive reasoning I told you about? A lot of times people, they just look at this number and they're like, that's my x, I'm going to plug it into my c, and this is my answer. Does that actually make sense to you? Like, find the actual cost of producing the 1,001st bag. Just that one bag, not like one all the way to 1,001. We're just talking about that one bag, not all of this. So this is a lot of money that you're talking about. That can't be how much one bag costs. It's probably all of these bags together. That's how much it costs. So what I should do is maybe figure out how much it costs for the rest of the bags up until 1,001, which is $140,431. And I think what I should do is probably subtract them. Okay, so in order to find the 1,001st bag, I'm probably going to take c to the 1,001 minus c to the 100, or 1,000. Which is about 0.432. Okay, so the cost of producing the 1,001st bag is 0.432. Oh, doesn't that sound like the last one? Pretty much like the last one. So why is that? Why are they actually pretty close in answer? Well, this one right here, if you're comparing 2 points, like technically, isn't this your y2? This is your y1. We subtracted those right here, didn't we? Our x2 and our x1, that's technically underneath, and isn't that a difference of 1? So what we did was we actually found a secant. And because the difference between these two numbers is actually so small, your secant is actually going to be very, very, very similar to an instantaneous rate of change, a tangent. And so this guy right here was actually a tangent, like an instantaneous rate of change. So this is your IROC, which is a tangent, right? Because you wanted it at exactly 1,000 versus this question, which was a secant. This is an AROC, an average rate of change between 2 points. And so again, because the 2 points are so close together in x value, you're actually going to get a very similar answer to the IROC. All right, let's try another question. This one I've actually done for you already, so I'm just going to explain it. This is our last example. Example number 3, Howard's Hamburgers estimates its cost by modeling, let's see, an original function, so right here. And market analysis showed that the demand function for its burgers is this price function, okay, or demand function, sorry. What is the demand for the hamburgers when the price is 2? So demand means what is my little p of x function, which I put in green before, when your x is 2. Okay, so I'm going to basically take my green function, set it equal to 2, and start to solve for x. So that's pretty easy. You just take this guy, multiply it to the other side, bring the 800,000 over, and you get x is 400,000. So when the price is $2, the demand for the hamburgers is going to be 400,000 burgers. Now the next part is asking, what is the marginal revenue when the demand is 300,000? Okay, so the revenue, marginal revenue, means, whoops, let's get rid of this. Again, I want to color code. So this guy is actually asking us for R prime of x. They're not asking us for the revenue, they want the marginal revenue. But I can't actually find R prime until I have R. And so we know that R is made up of x times our price per unit. Okay, so we have to multiply those two functions first. So I have x multiplied by p of x. Okay, so notice, let me get rid of those, that I had something like this. This x is going to multiply the 800,000 and then the negative x. So I get this next step, and I just decided to split this guy from this guy. All right, it makes taking the derivative a little bit easier when I don't have one big fraction. And so I like being able to break down these fractions and get something simple. This guy is still a little bit more complicated, so I'm just going to bring this and put it right beside, not into the denominator, just right beside. But now I can see their powers very easily. And so that means that if I want to take, say, the derivative now, I can do that for this term, which is just the 4, and then this one, which is just a power rule. Okay, I don't have to simplify any farther than that because I'm just going to sub in my x. So my x is going to be 300,000, which I'm then going to put into my x right here, and I get 1. This means that when the 300,000 burgers are actually sold, this company is, now remember, derivative means rate, is increasing because this one is a positive, increasing at a rate of $1 per burger. So if it was actually a negative one, you would say it would be decreasing by a rate of $1 per burger. And lastly, what is the marginal profit? Okay, so marginal profit, I think I had an orange. This guy was P, capital P, prime x. I can't actually find that until I find P of x. And so I have P of x right here. And that is made up of, your profits are made up of your revenue subtract your costs. So I have both of those functions. I remember finding, I think the cost function was given to you at the very, very beginning of the question. And then the revenue formula we actually found. Okay, so what I'm going to do is just make this look a little bit nicer before I take the derivative. What should I do? I should probably, you know what, I could write this guy at the beginning, right? I'm probably going to take this one, put it together with this one, and then just write that one at the end. Okay, so this is my P of x. It's in a nice row like a polynomial row, which makes it very easy to actually take the derivative right here. Okay, now after I take the derivative, they wanted it at 300,000 burgers. And so plugging in 300,000 into my x, I'm going to get about 0.58. So that means that when 300,000 burgers are sold, this company is increasing its profits at a rate of 0.58, which is 58 cents per burger. In the next video, which is going to be our last derivatives video, so our last Unit 6 video, we're actually going to go into position, velocity, and acceleration. Okay, so join me next time.